Today I am very happy to introduce my friend Thuy. She will talk about a very interesting problem, and she will talk about two-dimensional polynomial mappings at the infinity. So Thuy, please. Thank you very much for the invitation, for accept the invitation, and you can start now.
Okay. Thank you very much, Otoniel. So good morning, good afternoon, and good evening, everybody. At first, I would like to thank the organizers for the invitation. Especially thank you, Otoniel, for the invitation because giving a talk here for our webinar is very nice opportunity for me because on the one hand, I can record myself about some results on the topic of polynomial mappings. And on the other hand, it's very nice to share with you some of my ideas of my work in progress. And I hope that we can discuss and maybe I will have a good suggestion for continue this direction to study polynomial mapping. So allow me to start my talk now. So in this talk, we will talk about the Jacobian conjecture, and we will talk in both cases, real and complex. So the Jacobian conjecture, nowadays we know is this one. The statement is here that let f from Kn to Kn be a polynomial mapping. And here we consider K is the field of real complex and also field of real numbers and complex number in both cases. And here we consider F polynomial map. We mean each Fi here is a polynomial. And this conjecture says that if we have this condition, says that if the determinant of the Jacobian of the mapping is non-zero for every point in the source space, then F is an automorphism. So the statement of the conjectures is I think very easy to understand, but it is a until nowadays it is a mystery because in the case of dimension 1, you see that the conjecture is true, and it's very trivial because it's come from just linear algebra. But in the case of dimension 2, it is still open in the complex case. The conjecture was stated in the year 1939 by the German mathematician Otto Heinrich Keller, and until the year 1994, we had counterexample for the Jacobian conjecture in the real case of dimension 2 was given by the Russian mathematician Sergei Pinchuk. It means that just after 55 years after the Jacobian conjecture stated, we have a counterexample in the real case of dimension 2. But in the real case for dimension 3, the conjecture is still open. In the case of complex case, the conjecture is still open even of dimension 2. In dimension 1, it's trivial, but in the case of dimension 2, the conjecture is still open for the complex case. So we have another equivalent statement of the Jacobian conjecture that let f from Kn to Kn be a polynomial mapping. So this equivalent statement says that with the same condition than this condition here, we can replace the automorphisms of the mapping in the statement here by the properties of the mapping. So let us recall that the map F is proper if and only if its sum total set is empty. And the asymptotic set is defined as the set of deployed in the target space such that there exists a sequence in the source space tending to infinity, such that the image of the sequence tends to A. The sequence tends to infinity here, we mean the norm of the sequence tends to infinity. It means that the asymptotic set, it means that the mapping is not improper if there exists a sequences tending to infinity in the source space in such a way that it does not tend to infinity. And it's natural to study the asymptotic set of a polynomial mapping to approach the Jacobian conjecture, because from this statement we say that under this condition of the Jacobian conjecture, if F is proper, then the Jacobian conjecture is true. Otherwise, if we can find a mapping satisfying this condition and F is non-proper, then we can find a counterexample to the Jacobian conjecture. And the motivation of this work here is we would like to study a subset of a non-proper mappings and investigate the condition of the Jacobian conjecture of this subset. It means that we will give a class of non-proper mappings and we study the condition here in this class. If we can find a subclass in which a Jacobian conjecture is false for this subclass, it means that we can find a class in which the Jacobian conjecture is true. And here I would like to say that the study of the proper sets here was studied by mathematicians, especially by Chilonek, and he gave a complete description for the asymptotic set associated to a polynomial mapping in both real and complex cases. And here we study the asymptotic set also, but we look the asymptotic set with the other point of view. We study the behavior of tending infinity of the sequences in the source space. Okay. So the structure of my talk has the three parts. In the part one, we will talk about an asymptotic set approach for Jacobian conjecture in the case of dimension 2, in the real and complex cases in point of view here that we study the behaviors of tending infinity of the sequences in the source space. In the part 2, we will give some relations of our study in part 1 with the Newton polygon. And in part 3, we will talk very quickly about the intersection homology approach, about some results on the Jacobian conjecture using intersection homology. And I hope that I will have enough time to explain about a singularity associated to a pinch map and the calculation of intersection homology of this variety associated to a pinch map. Pinch map is a counterexample to the Jacobian conjecture in the real case of dimension 2. So in the part 1, we will study the asymptotic set of a polynomial mapping f from key 2 to key 2. Here we consider dimension 2. In both cases, real and complex. And we will introduce a new notion called pertinent variables. And this notion is to verify if a mapping is non-proper. So let me give you at first an example to explain the idea of pertinent variables. So I start with this example. F(y) is like this. So we can rewrite f as this one. You just put y here and we put x and minus xy here. And for the second one here, you just put 2y here, and this one is exactly x square minus x square y square on square here. So in this case, if you make a change of variables, u0 equal to y, u1 equal to x minus xy, u2 equal to x square minus x square y square. So f can be written under the other polynomial mapping of new variables u0, u1, and u2 like this. Y here is u0, this one is u1, this one is 2u0, and this one is u2 square. So we affirm that f is non-proper. Why? Because in this case, there is the sequence that is this one, such that u0, u1, and u2 of this sequence do not tend to infinity. It's very easy to calculate u0 of ck. In this case, u0 equal to y. So u0 of ck in this one is this one. So it tends to 1. u1 of ck, u1 is this one. So u1 is x times 1 minus y, and you replace yk here, and it's 10 to 0. And for u2 of ck, the same thing, very easy, you calculate, and in this case, u2 of ck tends to minus 1. So because u0, u1, u2 of ck do not tend to infinity, and f can be written under the polynomial mapping of these variables. So f of ck does not tend to infinity too. And this is the idea of pertinent variables. In this case, we call u0, u1, and u3 pertinent variables of the mapping. And the mapping f is called pertinent mapping. So pertinent variables is very simple. It's just a new variable in such a way that it's just a function from k2 to k, and this function is a non-proper function. Okay, it's just the idea, and it's the formal definition of pertinent variable. And a pertinent mapping is just a mapping that you can write it as a polynomial mapping under pertinent variables. Okay, and the first remark that comes from our example, and very easy to see that a pertinent mapping is a non-proper mapping. Remark 2, if a pertinent mapping does not satisfy the condition of the Jacobian conjecture, then it is not a counterexample to the Jacobian conjecture. Why? So let's go back to the statement of Jacobian conjecture here. So this one, you see that if you have this condition, we call it condition of the Jacobian conjecture, then the Jacobian conjecture say that f is proper. So go back to our remark here. A pertinent mapping is a non-proper mapping. So if a non-proper mapping do not satisfy the condition of the Jacobian conjecture, then it is not a counterexample to the Jacobian conjecture. And otherwise, if a pertinent mapping that satisfies the condition of the Jacobian conjecture, then this is a counterexample to the Jacobian conjecture. So let me use the diagram of Venn to illustrate the idea here. Here we have the set of polynomial maps, and here the subset of mappings satisfying the condition of the Jacobian conjecture. Here, the organs 1 is our set of pertinent maps, which are not proper mapping. Pertinent map here is non-proper mapping. So, this class, this is the difference of the map of the pertinent maps, but to take out the map with the condition of Jacobian conjecture. So this is the class in which the Jacobian conjecture is true. So if a map belonging to this class, the Jacobian conjecture is true. Otherwise, if a map in this class, this is a pertinent map, but satisfy the Jacobian condition, then it is a counterexample to the Jacobian conjecture. So the question is, there exists a map like this? And the answer is yes, but I will explain you later on. In the real case, the counterexample of pinchot, I will explain you later on that in fact there exists one here in the real case of dimension 2. Okay, so the natural question here is which under condition a pertinent map does not satisfy the Jacobian conjecture in the complex case and in the real case. We are studying, we don't know if the Jacobian conjecture is true or false. We hope that we will study a little bit about the Jacobian conjecture, but finding a counterexample to the complex case, for example, is a very difficult problem. So we would like to study a subclass here in which the Jacobian conjecture is true. So this question is we want to understand which condition such that our pertinent maps here does not satisfy the condition of Jacobian conjecture. And like this, we will provide some subclasses in which the Jacobian conjecture is true. This is the motivation of our work. So we would like to find some subsets in blue here in which the Jacobian conjecture is true. Okay. So the purpose of pertinent variables that we define here is natural that we would like to provide some sets of pertinent variables. Why? Because if you have a set of pertinent variables, you have a set of pertinent mappings. And like this, you have a set of non-proper mapping. And in this set of non-proper mapping, we will study the condition of the Jacobian conjecture, and we would like to understand which condition the pertinent mapping does not satisfy the condition of Jacobian conjecture. So in the part 2 of our purpose here, after providing you some sets of pertinent variables, so in each set of pertinent variables here, we will classify each set into two types. First one is dependent type, we call dependent type, and the second one is independent type. And in the class of dependent type here, we prove that a pertinent mapping will not satisfy the condition of Jacobian conjecture. And like this, we will provide you some subsets in which the Jacobian conjecture is true. Okay, so the first set of pertinent variables is exactly the generalization of the example that I gave you at the beginning. That is example f like this. F is a polynomial mapping under pertinent variables U0, U1, and U2. Here U0 is equal to y, U1 is s minus sy, and U2 is s square minus s square y square. And here we generalize this example with un here is the x power n minus b x nr y ns. Here in the generalization, we add more r and s here, where r and s are positive natural numbers. So this class is, I think that this is sufficient large enough because here r and s here are any positive natural numbers, and with these variables we prove that they are pertinent variables from key 2 to key. It means in both the real and complex cases. And another set of pertinent variables come from counterexample of pinch-out. So let me talk a little bit about the counterexample of pinch-out. It's a counterexample to the Jacobian conjecture in the dimension 2 of real case. Okay, here is real case, it's not complex case, real case. So pinch-out contrast, the counterexample is following. He take approach xy in R2 and he put t, h, and f is functions of variables of two variables xy. So t equal to xy minus 1, h to e is equal to t times ht plus y plus 1, and f is this function of variables h, t, and y. So he's put p, the mapping in which the first coordinate p here is the sum of f is here and h here, and q is complicated. Q is these functions of three variables t, h, and f. And pinch-out proved that in this case the determinant of the Jacobian of the mapping P is always strictly positive, but F is not injective. So this is a counter example to the Jacobian conjecture in the real case of dimension 2, because you see that this condition is exactly this condition in the real case. I mean, not exactly, but satisfies, because you can say that the determinant of Jacobian is strictly negative. But see here, the determinant of Jacobian of the mapping is strictly positive. So the condition of Jacobian conjecture satisfied. But F is not injective, because in the conjecture they say that under this condition, then the mapping is automorphism. And this is a counterexample of pinch-out that he provided in the year 1994. And that means just after 55 years after the Jacobian conjecture stated. And it's very interesting that Professor David Trotman, he told me that pinch-out discovered this counterexample in Marseille, in France. And he told me that one occasion, pinch-out visited Lumini in Marseille and worked there. And in this occasion, pinch-out discovered this counterexample in Marseille, in France. So, and I would like to say also that pinch-out, he constructed a classes of counterexample to the real case of in the case of dimension 2. And here I just show you the smallest degree, and in this case the degree of pinch mass is 25. Okay, so now we affirm that the variables t, h, and f here are pertinent variables. Why? Because in this case, this sequence. This sequence is clear that it tends to infinity. But if you calculate t of ck here is equal to sy, this case is 1 minus 1 is 0. So t is equal to 0. Then tck tends to 0. So you calculate h of ck because t equal to 0. So h of ck tends to 0 is clear. So now f of ck, t equal to 0. So the first factor here is 1 and the second one is y. But y in this case is 1 over k. So fck tends to 0 too. So it means that in this case we can we can find a sequence tending to infinity, but t, h, and f of this sequence do not tend to infinity. So with our definition, t, h, and f are pertinent variables, and we call t, h, and f the pinch pertinent variables. Okay, and in this case, the pinch map here is a pertinent map. We note that in this case, t, h, and f are also pertinent variables in the complex case. I mean, if you change r here by c, you have also a mapping, and in this case, t, h, and f are also pertinent variables. But we note that the pinch counterexample here is just for the real case. It is not a counterexample for the complex case. Why? Because in this counterexample, the determinant of Jacobian of the pinch mark here is a polynomial, and pinch prove that in this case, this one is a sum of some squares of polynomials, and it is strictly positive. But this polynomial has solution in the complex case. So this condition satisfies the condition of Jacobian conjecture in the real case, but in the complex case, it does not satisfy. Okay? Okay. And it's exactly as the diagram of Venn that I draw at the beginning. There is a mapping here, which is a pertinent map and satisfies the condition of Jacobian conjecture. This is a pinch map, and is in this class of pertinent maps, but satisfies the condition of Jacobian conjecture. Okay. So now we continue our motivation of the course. We would like to classify the pertinent variables into two types. The first one we call dependent type, and the second one is independent type. And the definition, the formal definition is like this. We consider U0, U1, Un pertinent variables. We say that they are dependent if there exists a point in the subspace in such a way that these two vectors are linearly dependent. These two vectors, what are they? The first one is just the partial derivative of the pertinent variables at the point z with respect to the first variable x. And the second one is the same, but we consider with the second variable y. And we say that these variables are dependent if these two vectors are linearly dependent. Otherwise, they are independent. And from this formal definition, it is not very difficult to prove that if U0 until UN are dependent, then any pertinent mapping of these dependent variables does not satisfy the condition of the Jacobian conjecture. So it's the reason why we would like to find some class of dependent variables so that we have some subsets in which a Jacobian conjecture is true. So our result is in this theorem that we consider the set of pertinent variables is exactly the generalization of our example at the beginning, this class of pertinent variables. And we prove that when R equal to 1, independent with this number S, the pertinent variables here are dependent. And if R is greater than 1, what happens? If R is greater than 1, so we prove that for a fixed natural number n here, the pertinent variables here are independent. So what does it mean, this theorem? The theorem says that if we put CR is our class C intersects with the class of the mapping F in which F satisfies the Jacobian conjecture, then CR equal to empty set, we obtain a class in which the Jacobian conjecture is true. Okay? And if CR is not empty set, we can find a counterexample to the Jacobian conjecture. So natural question is when CR is empty set, and in this theorem says that C1 is empty set. That means that we get a class in which the Jacobian conjecture is true. Independent with S here, you can put any number S here and just R equal to 1, we get a class in which the Jacobian conjecture is true. And when R is greater than 1, so we get a class of pertinent variables, and we know they are independent, but we don't know if they satisfy the Jacobian condition or not. So it's natural that we will study the condition of the Jacobian conjecture of this class of independent variables. And we continue with pinch-truth pertinent variables, and we prove that they are independent also in both the real and complex cases. The pinch-truth pertinent variables I recall you here in the example of pinch-truth. It is clear that these variables are independent because the condition of Jacobian conjecture satisfies. So it's clear that they are independent because with our definition, if you have dependent variables, then the Jacobian condition does not satisfy. And in this proposition, we prove that the pinch-truth pertinent variables are also independent in the complex case. So this work is in progress, and until now we have two directions to continue to study Jacobian conjecture in this study, with this direction of study. that now we have two classes of independent pertinent variables. The first one is the generalization of our example with the case R is greater than 2. And the second one is the set of input pertinence variables here. So we will study the condition of Jacobian conjecture of a pertinent polynomial mapping written under these independent pertinent variables. Because in the case dependent it is shown is true, and in the case of independent, we would like to understand more about the condition of the Jacobian conjecture. So we have two directions to study in the real case and in the complex case. In the real case, our questions is, we know that counterexample of pinchut has the smallest degree is 25, the one that I presented you. So our question is, what happens with mappings of degree less than 25? Polynomial mapping of two variables in the real case, if its degrees is less than 25, then the Jacobian conjecture is true or false. So this question. So in this paper, Bruna and Francisco and the Federal University in Sao Carlos, they prove that the Jacobian conjecture in the real case of dimension 2 is true for degree 4. So our question is study the condition of Jacobian conjecture of two independent pertinence mapping that we provide above, but in the case degree greater than 4 and less than 25. And we see that with pertinent variables that we provide here, when we work with these pertinent variables, we can reduce the degree of mapping. For example, in this case, the degree of H is 5, degree of F is 10, and degree of T is 2. If you work with these variables, a mapping of degree 25, we can reduce it to a mapping of degree 2 for some. Okay. And the second direction to study for the complex case is, so let me recall you some principal results in the complex case, and after that we will tell you what direction that we are going to study. So the complex case, we consider F from C2 to C2. This result of the Indian mathematician Abhyanka say that if degree of F here divide the degree of G, or degree of G divide the degree of F, then the conjecture is true. And this result say that if the greatest common divisor of degree of F and G is less than 9 or is a prime number, then the conjecture is true. And this result here of the Chinese mathematician Nagata is say that if degree of F or degree of G here is product of at most 2 prime numbers, then the conjecture is true. And this result is very strong that the conjecture in the complex case of dimension 2 is true if degree of F is less than 102. So the question here is, what happens if degree of F is 102? So let me do a little calculation here to see what happened, what possibilities that we can consider in this case of degree of the mapping is 102. So we assume that the map have degree 102, So we know that the degree of each f, small f and g here are less than or equal to 102. So we fix the degree of g is 102. And we will determine all the possibilities of degree of f here. So we see that 102 equal to 6 times 17. So in the case if degree of f is divisible by 17, then the greatest common divisor of degree of f and g is less than 6 because we have this one. And you use the result here. The second one, if the greatest common divisor of degree of f and g is less than 9, then the conjecture is true. So in this case, the conjecture is true. So we need to consider just in the case degree of f is divisible by 17. So in this case, you have just 6 possibilities here. But for the first 4 possibilities, for this possibility of 17, 35, 51, and 85, then this case, degree of f is product of 2 prime numbers. So we use the result here. If degree f is a product of 2 prime numbers, the conjecture is true. So we don't need to consider this case. Now we consider degree of f is 102. And in this case, degree of f and degree of g are equal because we fix degree of f is 102 here. So we use the result here. The first one, if degree f divide the degree g, then the conjecture is true. So this case we do not consider 2. So the only case, in the case of degree of f is 102, we need to consider is a degree of the first polynomial f is 68 and degree of g is 102. Just one possibility that we need to consider in this case. So our problem that we would like to study in the complex case that we study the condition of Jacobian conjecture of a pertinent mapping with the respect to independent pertinent variables that we provided you before. In the case of degree f and degree g is this one. And we go back to our 2 class of independent variables here. For example, with the pincher pertinent variables, degree of f is 10. So if you consider a mapping of degree 68 here, the degree of the mapping reduced to 6. But even that is difficult. I think that we will need some program, some program to calculate the Jacobian condition, something like this. And it's just idea we are going to study the conjecture with this direction and continue to calculate the determinant of the Jacobian of the mapping to understand. Okay. So I would like to say that the idea of pertinent variables came the first time when I did my PhD thesis, and in this time I would like to classify the asymptotic set. So I would like to understand the behavior of tending to infinity of the sequences in the source space, and it came the idea of pertinent variables to classifies the behaviors of tending to infinity of the sequences. And I wrote out the idea in this paper that I put in arXiv in 2 years ago. But all the definition, formal definition, and the classify the pertinent variables here that I have just presented you here. It comes a lot from discussions with Professor Luis Renato at the University Uberlândia in Brazil. That one time I went there and I have some day in university and I discussed with him, and we worked a little bit together, and we discussed how to formalize the idea, and it's come from discussion, a lot of useful discussion with Luis Renato. Okay, so now I would like to go to part 2, that I will talk very quickly about some relations of our result in part 1 with Newton polygon approach. So Newton polygon approach is for studying the Jacobian conjecture in the complex case of dimension 2 was given by Indian mathematician Abhianka in the year 1977, and after that there are many mathematicians continue to study with this direction. And in here I just recall the two-dimensional complex Jacobian conjecture is the ones here, and we note that in this case the Jacobian condition can be stated as the determinant of Jacobian of the mapping is always constant, different from 0. And from now I would like to call in fact we call a mapping satisfying this condition Euclidean map. So let's call a mapping that satisfies the condition Euclidean map to be easy to explain the result and the idea. Okay, so as first the definition of Newton polygon is the following. Newton polygon is defined for a polynomial of two variables x and y. Here we consider the complex case. Then if you have a polynomial mapping, a polynomial, now it is not a polynomial mapping, it's a polynomial. So we can write f as a finite sum, is this one, and we divide the supporter of f is the set of exponents of monomials of f. And the Newton polygon is the convex hue of the support of f union the origin. So let me give you some example. So for example, in this example with the polynomial here, this project x gives you the project 1, 0, this project, this x square gives you the project 2, 0, this one gives you the project 1, 1, this gives you the project 0, 1, and this one gives you the project 0, 2. So you take the convex whole of this project, but don't forget the origin, and you get Newton polygon. In this case is a triangle. The second example, here x gives you 1, 0, x square y gives you 2, 1, x y gives you 1, 1, x y square gives you 1, 2, and y gives you 0, 1. And don't forget the origin, and you take the convex whole, you get Newton polygon. In this case is a pentagon like this. Okay. We have a very nice resource about a similarity of Newton polygons was given independent by Indian mathematician Abhyanka and the American mathematician Raza here, saying that in the case of degree f and tree here are greater than 1, then the Newton polygon of a Euler map of f and tree are similar in such a way like I draw in picture here. Okay, and it's very nice resource because to study the Jacobian conjecture, instead of study the Newton polygon of the two polynomials f and tree, you need to study just one because they are similar. So it's a nice result. And after that, Abhyanka, he gave this theorem saying that if you have a Euler map,
yeah. Sorry. Similar means there exists a homotopy between them. Yeah.
It means that one triangle is often from the other one, the other by a similarity transformation of the origin is the origin here and of the radius positive here. And in the theorem of Abhyanka, he gave also explicitly the radius, what is the radius here with the respect of degree of f and g.
My question is, similarity means homotopy is the same? What is similarity transformation? What do you mean by that?
Here I mean that it's just similar is transformation, but in this sense that you have a Newton polygon, for example, in energy here. So you fix the origin here. Is the origin, and we have the radius r is greater than 1, 0 here. So you can transform, for example, this h of energy and this s of nf. You have the radial r, and for the other other s and vertices of the Newton polygon too.
Thank you. Sorry.
I see that in my figure here is not very exactly. The ratio here is must be the same. So this is very a good question that I have to correct my figure here. So it's what with the same that you have the same radio here.
Okay.
The radio here in the theorem of Abhyanka, he gave also what is the radio here. The radio here is with the respect to the degree of f and g that I don't write here, but you are right that this figure is not very exactly the radio here. Yeah. So sorry, but it's still okay. Yeah. Thank you very much for the question. Okay, so now this theorem of Abhyanka says that if we have the Euler map and the Newton polygon of f is the triangle of this form, that means that we need to have 2h in the coordinate axis. Then the mapping f is invertible. That means that if you have a Euler map and the Newton polygon of the map, Newton polygon of each polynomial here, is a triangle like this, then you have a class of mapping in which the Jacobian conjecture is true. Here you need to know that if the Newton polygon of f is a triangle, because with this theorem of Abhyanka, if you have the Euler map and the Newton polygon of f is triangles, then Newton polygon of G is also triangle. So It means that we have a class in which the Jacobian conjecture is true. We call it the Abianca class. It's a class of Keller maps such that Newton polygon of F or G is triangle. Okay, as in the figure here. So we go back to our result. So our result here, we have a class in which the Jacobian conjecture is true. In terms of pertinent variables, if a mapping is written a variables here, then our map is a map in which the Jacobian conjecture is true. So the question is, describe the Newton polygon of a pertinent mapping here. So our pertinent variables is that this. So in general, UN is this one. So you see that UN, the support of UN, live always on the vertical line of equation I equal to n. You see in this form. So if you take the power of UN, or you take a mixed term U I, UJ, so the support is always in the vertical line. And for U0 with Y here, it gives you the support is projected on the coordinate vertical line here. If you take the power of U0, so you have more point here in this vertical line. So the Newton polygon of our pertinent mapping is a triangle like this. If you don't have U0, so you have a triangle like this. And we must have the ratio of the HAB and BC here is S, because UN in general is like this, is equal to S for a fixed S that you fix at the beginning. Okay, and in the case that you have you have pertinent variable U0, so you have more approach here in this line. So in this case, you get Newton polygon. For example, in the figure, is the trapezoid A, B, C, D. But in general, we may have also pentagon, hexagon, but our Newton polygon must be of the form that you have one edge is in the horizontal line here, horizontal coordinate X here, and one is in the line here, and the other one is the vertical line here, that's a parallel to the vertical coordinate X. That's our class of in which the Jacobian conjecture is true in terms of Newton polygon. So we compare with the Abianca class. So Abianca class is the Keller map with Newton polygon like this. And for complex case, our class that we don't need the mapping satisfies the condition of Jacobian conjecture. And if you have a Newton polygon of this form, triangle or polygon like this, so you get a mapping in which a Jacobian conjecture is true. But our class, we have to verify for both F and for both polynomials F and G of the mapping. And Abianca, he needs just to verify one Newton polygon, because in this case, Newton polygon are similar. And here we get a class of non-Keller and non-proper, so that the Jacobian conjecture is true. And our class is for both cases real and complex, because if you define Newton polygon in the real case is okay too. And because our results is for real and complex cases, so the class here are for both real and complex cases. Okay. Now I hope that I have time to talk quickly about intersection homology. I don't know how much time I have now.
Do you have time? Go ahead. No problem.
So I need more 10 minutes. Is it okay?
It's okay, Thuy. It's okay.
Okay, thank you. So I would like to talk very quickly about some results on the intersection homology to approach the Jacobian conjecture. Using intersection homology to approach the Jacobian conjecture was first given by Anna Vallet and Guillaume Vallet in the first paper, very nice paper here, first appeared in the year 2010 in Archive, and after that they published in this very nice journal in the year 2014, and here Anna and Guillaume Vallet, they constructed a singular variety from C2 to C2, and this polynomial satisfies the condition of the Jacobian conjecture. And they say that under the condition of the Jacobian conjecture that here, so the intersection homology of the variety that is constructed gave an equivalent condition for the dysmorphism of the mapping. It means that they gave another equivalent statement to the Jacobian conjecture using intersection homology. So we have just seen that to verify if the Jacobian conjecture is true, we can study the properties of the mapping. And here, with the variety that Anna Vallet and Guillaume Vallet constructed, they say that the triviality of the intersection homology of the variety that is constructed is equivalent to the diffeomorphic of the mapping under the condition of the Jacobian conjecture. So with them, we generalize this result in the case of any dimension, because it results is for Jacobian conjecture in the complex case of dimension 2. And we prove that the result of Anna and Guillaume Vallet holds also in the general case of any dimension, but we need more at the additional condition that the flux at infinity of the fiber of F are complete intersection. And the results in detail like this, here I just write out in details to say what we mean the plot as infinity of the fibers of F are complete intersection. This one in red. Okay. And after that, we got Professor Maria Aparecida Suarez, who was Professor Sirinya, that everyone know. We developed the result in the case of Cn to Cn to the case of Cn to Cn minus 1. That means that we modify the construction of the variety of Vallet here in the case from Cn to Cn minus 1, which is a case that the singularities of the mapping may be more complicated, and we modify the construction of the set Vg, the Vallet set that Vallet and Anna constructed, and with this with this new version of singular variety Vg, we show that we can use the intersection homology of this variety to study the bifurcation set of the mapping G from Cn to Cn minus 1. And here in this result, we prove for the general case that the intersection homology of the singular variety contrasted here, BG here. Then we give a sufficient condition such that the bifurcation set BG of the mapping is empty. Here, the triviality of the intersection homology of the contrasted singular variety give sufficient condition for the emptiness of the bifurcation set BG. This result is similar to this result of Hà Huy Vui and Nguyễn Tất Thắng, two Vietnamese in the year 2011. But the difference that in this theorem, Hà Huy Vui and Nguyễn Tất Thắng, they use the Euler characteristic of the fibers of the mapping. And here we give another version of the result using intersection homology. This problem of studying the bifurcation set of the mapping from Cn to Cn-1 was started to study since the year 1974 by a Japanese mathematician Suzuki, and after that it was resolved by Hà Huy Vui, Vietnamese mathematician, and Lê Dũng Tráng, everyone knows him. And in this work, they resolved the problem in the case from C2 to C. And what they use is Lojacki-Awicz inequality. And until the year 2011, Hà Huy Vui and Nguyễn Tất Thắng give the complete result for the general case. Okay, now I will give. I talk a lot about the singularity contrasted by Anna and Guillaume Valette here, but I did not talk you what is the contraction of this variety. So now it's time that I talk a little bit about the contraction of Valette variety, and after that I will give you a Valette variety associated to a pinch map. So I will give you an example, so it's very quick. So for example, we consider this mapping. And the idea of Guillaume and Anna Valette is the following. At first, you calculate the singular locus of F. Singular locus of F is the set of solution of the Jacobian of F. And in this case, the singular locus is union of two lines. The line x equal to 0 is a vertical line, and the line y equal to 1, the blue one that I draw here. And after that, you calculate K0f is the image of singular f. It's known as discriminant of f. So in this case, we calculate the image of sin f, and it's in the parabola K0f here. And you calculate the asymptotic set of f in this case. And it's very easy to calculate. In this case, the asymptotic set of the mapping is the red one here. The idea of Anna and Guillaume Valette is in the source space, the singular locus F divided the source space in four regions. U1 here, U2 here, U3 here, and U4 here. And after that, they calculate the image of U1, U2, U3, U4 here. For example, he calculates FU1 and FU2, and they see that FU1 and FU2 in this case are coincident. So they want to separate them. So they need to use a technique called the Mostoki separation lemma. So they separate FU1, FU2 in a higher dimensional space. So they need to add more some dimension, and they leave each part in a higher dimensional space for each FU1 and FU2 here. And after that, they glue them together. And and they get a singular variety, something like this. And they prove that in this case, the singular locus of the singular variety that they constructed is the union of the discriminant of the mapping with the asymptotic set of the mapping. So now we go back to the pinch map. So we know that the pinch map here is the map that the Jacobian conjecture satisfy. So in our case, the set of discriminant of the mapping is empty. So to construct the valid variety, I need to understand what is the asymptotic set of the pinch map. But the asymptotic variety of pinch map was studied completely by the American mathematician Andrew Campbell, and he described the asymptotic variety is this one, this curve. And after that, he calculated the inverse image of the asymptotic variety in the source space is 3 curves. So I will show you in this picture in detail that it is the asymptotic variety. So it's a curve that has singular point here and has origin here. So Andrew Campbell, he said that this point, singular point, and the origin here break the curve here in the target space into 3 curves in the target space, and this is the inverse image of the asymptotic variety. And Andrew Campbell, he called this is asymptotic flower. Very beautiful, I think. And to calculate valid variety of pinch map, I need to calculate the image of the regions that the image that the inverse image here divide the source space in 4 parts, as you see here. This one, above this one, and this small one, and this one. And I calculate the image of these regions, and I get valid variety is something like this. You have the regions are glued together along the asymptotic set. And in this case, the blue one here and the blue one here are glued together at infinity. And this I calculate the intersection homology in both the cases, closed support and compact support. In the case of closed support, I have allowable trend is this one or this one. And in this case, this trend bound to something. So we get homology, the intersection homology is 0. And in the case of compact support, I have this trend is allowable. And it bound something too in this case. So in both cases, we get the intersection homology of valid variety associated to pinch map is trivial. And this is a counterexample for valid result in real case, because in the complex case, valid says that under the condition of Jacobian conjecture, then the intersection homology is trivial. But here with pinch map, we don't we have the mapping is the mapping satisfies the condition of Jacobian conjecture, but the map is not diffeomorphism. And in this case, if you use the result of Anna and Guillaume-Ballet, the intersection homology here should be different from should be not trivial. Should be not trivial, right? And here we show that the intersection homology is trivial. So it's show that the real person of Anna and Violet is no longer true. So I think that I finished talk here. Thank you very much for your listening and attention. Muito obrigada and thank you. Cảm ơn các bạn rất nhiều.